All right, so currently you have been solving trigonometric equations using quadratic techniques and using simple special right triangle relationships. This second video is going to focus on solving trigonometric equations with transformations and getting us to realize what we are doing when we're undoing the transformations. The biggest thing I want, and me and Mrs. Kleiss want you to think about when looking at these is you are basically undoing all of the transformations that we learned in Unit 5. And what I mean by that is on this next slide. So the difference between the two trigonometric equations below is extremely important to know on what am I doing in expression 1 or equation 1 compared to equation 2. So like before, the a value on the functions was the amplitude, how tall the wave kind of cycled. Since we know the waves are looking like this, the a value is talking about how big the amplitude is from the midline. And then the b value is talking about how long does it take until a period starts repeating. Now, if you notice, the two most important ones are going to be the h and the k function. And that k value is the midline that cuts the graph in half. So realizing what's the difference between what a number is and a k, when can we use the operation to solve, and when it's on the inside. So if you look at, I want to relate it back to something we've done previously before. If you look at when you solve this question, when I look to solve this question, my first step is to isolate the radical and then to get rid of it. So we take, right now, I can't subtract 3 because the plus 3 is underneath the radicand. So in order to get rid of the radical, we have to square both sides, and then you get x plus 3 is equal to 0, and you get x is equal to negative 3. And that's my solution there. So in other words, I'm taking the inverse of a square root is squared. Where on this one, my first step is that I have to isolate this expression first, so then it becomes the square root of x equals negative 3, and then I square both sides. So then you take the inverse. So the difference between this one is that my first step is that I need to square both sides. In other words, take the inverse. Where on the second one, I needed to undo the transformation first of moving up 3, so I move it back on the other side, and then I square both sides. Now, how that relates to the one up here is that if you look at right now, the 2 value on both these functions is the amplitude. It does not affect anything to do with the graph when it comes to solving. Our first step would be divide by 2, and then you get cosine of x plus 3 equals 0. And over here you get, our first step over here would be divide by 2, and you get the cosine of x plus 3 equals 2. Over here, though, however, the difference is, let's get rid of this actually, it's the fact that our x plus 3 is a function at which it's on the inside. So this 3 here is our h value. So it's our horizontal movement that's transforming the cosine graph. So we're moving, this graph is going left and right 3 units. So in this case, it's going to shift to the left 3 because of being plus 3. Where in this graph, this 3 isn't the h value, this 3 value is the k value, which means we're moving up or down. Now you wonder how this relates, is that on the inside here, this took the graph and moved it left or right. And on this graph here with the 3 on the outside is going to move it up or down. So it's the same thing with the cosine graph. Since this graph is moving up and down, what I need to do is I need to isolate this function right here. Kind of like how we did before. Our first step would be to subtract 3 to get 2 cosine of x is equal to negative 3, and then you get cosine of x is equal to -3/2. We'll talk about how we're going to undo that. Or in this one, I can still divide by 2, but I'm going to get cosine of x plus 3 is equal to 0. And now I can't subtract the 3 because it's inside the parentheses. So my operator is this whole function. Where here my operator was this whole function. So what I just boxed in here is equivalent to what this is down there. I couldn't do anything inside the radical or the radicand here until I took the inverse. I can't do anything inside of this to find x until I take the inverse. Or here, since it's just a square root of x, it's already isolated, it's by itself, there's no transformation left or right, there's no period change, I can just subtract 3 divided by 2 like you've done in previous lessons. So our idea now is that at this point, we're going to kind of think of this as, let's switch colors here, we're going to go cosine, I'm going to think of this as cosine of z equals 0. I'm going to evaluate where does the cosine of z equals 0. I'm going to treat this like it's a separate variable, but z in this case is equal to x plus 3. When I go back and solve this, and which we'll talk about in the next slide. So I'm going to think of this as, now I got this isolated, now I'm going to find my values. So let's kind of put all of this together right now. So looking at the function here, in this example, I'm just going to show you everything and walk through a little bit, is we're going to find the values that are going to be done in radian form. So my answers will always be between 0 and 2 pi, expressed in terms of using pi. So if you notice, our first step was always to isolate the trigonometric function. So I'll kind of give you a little picture here. It should be trig values, sine, cosine, tangent, cosecant, secant of a set number. In some cases, like previously, it's been very isolated. But now with these next ones, we got to get to the point where we're just going to try and isolate this function by itself. So what I did was, is I let z represent the whole trig function of what the transformation is. So the x plus 3, or the theta plus 3. This should be a theta. So I treat this as I divide by 5, I get -1. And now I'm just going to solve this expression like we've done before and say, where does cosine of z equal -1? So this is my sine analysis. I know that cosine is negative in quadrants 2 and quadrants 3. And then I ask myself, where is the cosine equal to -1? And the only answer that it's equal to is pi. And previously in all those other lessons we've been done. And the reason we would be done at this point right here would be if this was cosine, the original was 5 cosine of z equals -5, and we're just solving for z, then yes, that would be my answer. But since we have this theta plus 3, this x plus 3, we have to undo that transformation. So our new step is that as soon as you get your answer, even if it was, let's say, a second answer, let's say we had pi and then 2 pi, we would set both of these answers back equal to what the transformation was. So here I did is I set pi, took my solution that I found, I set it equal to x plus 3. And I solve for x because I'm looking to see what value of x is going to make this statement true. And then I subtract 3 and I get x is equal to pi minus 3. Or in other words, 3.14 minus 3, which is roughly 0.14. 0.14 is roughly what I'm going to be able to plug into this solution in for theta and get -5. So if I were to punch this in my calculator or punch this on any other device we're trying to look at to see if this is correct, I put, making sure that I'm in radian mode, I go 0.14 plus 3, which I get 3.14. Cosine of 3.14, so what's the cosine of pi? Becomes -1. -1 times 5 is then -5. So our new step is all that after we've done before, all of everything up here, we're just going to basically put a big Z or a big Y or a big P or a big Q It's kind of like a substitution. We're like substituting this. We're going to isolate this trigonometric function. So we're going to treat it like it's a big random, or not random, set cosine, set sine, set tangent. And then we'll undo the transformation, the very last thing we do. So just keep in mind the solution is a given function in which you have transformed this function back to its given parent function of cosine of x. So in other words, you took out the amplitude value, you took out the cosine, the operator. In other words, you took cosine inverse of that value, and then you undo the transformation. So another one, just to kind of walk through again, is again looking to be in radian mode between 0 and 2 pi. And this is square root of 3 cosecant of theta minus 2 is equal to negative 2. So I'm going to take z. Z is probably my favorite variable to use. A capital letter z. I'm going to replace this whole function here with the capital letter z, which gives me this. So now I'm going to perform step 1. Step 1 is to isolate the cosecant of z. So I subtract or divide by square root of 3. After I divide it by square root of 3, I get negative 2 over square root of 3. And since this is a reciprocal function, I take the reciprocal of cosecant, which is sine. So I think sine of z is equal to negative square root of 3 over 2. And now this is where I'm using my unit circle. I'm going to do my sign analysis. Where is sine negative? Sine is negative in quadrants 3 and quadrants 4. And then, more importantly, I know that sine is opposite over hypotenuse. So that means square root of 3 over 2. What is always opposite square root of 3 is a 60-degree angle. So my reference angle is going to be pi over 3, or 60 degrees. So therefore, quadrant 3, then I would add pi to get 4 pi over 3. And in quadrant 4, I take 2 pi minus pi to get 5 pi over 3. If these are my answers, when it's a cosecant of z equals whatever, or sine of z equals the value. But because I have this transformation that I have not done anything with, my new and final step is I take my answer, 4 pi over 3, set it equal to theta over 2. I set 5 pi over 3, set it equal to theta minus 2. I'm then going to add 2 to get theta is equal to 4 pi over 3 plus 2, which is equivalent to about 6.18879. And then the second one, I'm going to add 2 to get 5 pi over 3 plus 2, and I get 7.2359. So these technically are our two answers. But because my restriction says between 0 and 2 pi, and 2 pi is about 6.28, we realize that since this value is bigger than 6.28, I have to find a coterminal, or I have to find a value that's between 0 and 6.28, so I had to subtract the 2 pi. So this only happens a couple times. This doesn't happen very often. But in this answer here, these would be your two answers, the one that are in red. You'd have 6.18, which went from a quadrant 3 that has shifted to quadrant 4, because picture-wise, we're down here, and then since I'm adding 2 radians, it's moving it there. And then you look at the second one, which was in quadrant 4, and now you're adding 2 to it. It's gone beyond, and now it's this value. So it's actually, your final answer ends up being up in quadrant 1, and this final answer ends up being in quadrant 4, but originally it started in quadrant 3 and quadrant 4. This only happens, you got to make sure that their values fall between 0 and 6.28. If they go over that, you got to find a coterminal. So subtract 2 pi, or subtract 360 degrees. So the only new step that we're adding with this is that now, as soon as you find your answer, you're going to set it equal to that transformation. So in a way, if we go back to this slide, if I've got a number here, I'm going to subtract the k, I'm going to divide by a to get this whole cosine function right here by itself, and then I'm going to take the inverse and set that answer equal to that.